Welcome to The Explainer. Today, we are talking about one single number. A number so fundamental that it literally shapes the destiny of every living population on this planet, from the tiniest insects all the way up to us. So let me ask you this. What single number could possibly predict whether a species is going to boom or bust or just stay the same? It's a number that ecologists, conservationists, you name it, they obsess over this thing for a very good reason. And that number is tied to this concept, the replacement rate. It's actually a pretty simple idea when you break it down. Think of it like the ultimate biological break-even point. For any population to just keep going, each female has to produce enough offspring that survive to adulthood to replace herself and, of course, her mate. Which brings us to the magic number itself. 2.0. 2. Seems so simple, doesn't it? But that number, that's the razor's edge. That's the tipping point on which the fate of an entire species rests. Okay, so the rule itself is pretty straightforward. If you're below 2.0, you're shrinking. If you're above 2.0, you're growing. And right on the line, you're stable. But here's the kicker. It's not about big changes. The truly mind-blowing part is how sensitive the whole system is. A tiny, tiny shift away from that line doesn't just nudge the population. Oh no. Over time, it creates these massive compounding ripples. So to really see this in action, let's just look at a simple but pretty eye-opening model. We're going to use 3 different animals to make the point. All right, so picture this. We've got 3 different populations, let's say 100,000 of each. Now, the only thing we're changing is the average number of surviving offspring per female. For our mice, that number's just a little low, 1.9. For the rabbits, they are perfectly balanced right at 2.0. And for the deer, they're just a hair above, at 2.1. Now let's see what happens when we let this play out for just 20 generations. And the results? They're staggering. The mouse population, with that tiny deficit, it just collapses. It's down by 64%. The rabbits, right on the money at 2.0, they're perfectly stable, no change. But the deer, whoa, their population explodes, growing by 165%. And remember, the difference between total collapse and a massive explosion was just a tiny 0.2 points.
This right here, this is the whole story. It's the incredible sensitivity of the system. We're talking about a change of just 0.1. And these populations don't just drift apart, they diverge wildly. It all comes down to what the source material calls just a little more or a little less. It's not a slow drift, it's like a rocket ship or a rock, taking off in completely opposite directions with every single generation.
So, okay, this works in a clean, simple animal model. But what about in the real world? What about us? I mean, does this same mathematical tightrope walk apply to our own, complicated, messy human history? Well, the answer is a huge yes. When you look back at 3,000 years of data, you see that humanity has gone through these really distinct phases, and they're all defined by this number. For most of our recorded history, we were just hovering right around that 2.0 mark. Then, wham! The industrial and medical revolutions hit, our survival rate shot way up, and the population surged. And now? Well, now, we're seeing a global trend back toward that 2.0 line. It is truly incredible to look at our own history this way. For thousands of years, humanity was in this state of near-perfect balance, just barely replacing itself generation after generation. And then, in what is basically the blink of a cosmic eye, this massive spike happened, and it completely reshaped our entire world in just a few hundred years. So why should you care about all this? Well, because getting a grip on this delicate balance is absolutely essential for tackling some of the biggest challenges we face today. Think about it. This one number is at the heart of 2 massive ecological puzzles. On one hand, you have endangered species. For them, the entire goal of conservation is to just nudge their survival rate just a tiny bit above that 2.0 line. That's all it takes for recovery. But then you flip the coin. For invasive species, the problem is the exact opposite. Their survival rate is just slightly above 2.0, and that's what allows them to just explode and completely take over ecosystems. Same math, wildly different problems. Now, of course, we have to be clear. This is a simplified model. In the real world, things are way more complex. You've got migration, you've got limits on food and space, you have different age structures in a population. All that stuff matters a lot. But the real power of a model like this is that it strips all of that complexity away to show us the raw, undeniable power of one single factor, the pure mathematics of replacement. So I think the biggest takeaway here isn't just about the numbers themselves. It's really about recognizing the quiet, almost invisible power that these small, sustained changes can have over time. And as the source material so perfectly puts it, it's these tiny little deviations from the 2.0 line that end up sculpting the destiny of a population. It's a powerful reminder that the biggest, most important long-term trends are often driven by forces we can barely even notice day to day. And that really brings us right back to today and leaves us with a pretty provocative thought. As fertility rates around the world start to drift back towards that 2.0 line, we are entering a totally new chapter in the human story. So what comes next? A new era of stability? A slow, managed decline? Or maybe something else entirely that we haven't even thought of? The next chapter is being written right now, one birth at a time.